Welcome back, folks. Last time we talked about using the normal distribution to find probabilities about samples of proportions. This week, we're going to talk about how we can use the normal distribution as an approximation for the binomial distribution. So we talked about the binomial distribution a few weeks ago. And so we're going to talk about how to use the normal distribution to answer similar types of questions and use it as an approximation to saving a lot of calculations in terms of the binomial distribution. So recall that we had the mean and standard deviation of a random binomial variable. At the mean, the expected value is just n times the probability, or I'm sorry, n times the probability of success. Okay, and then the standard deviation was just calculated this way. And then we found the probabilities of X number of successes this way. You should recall this because there was an Excel project on it, right? Where you use this formula multiple times in multiple different ways. So let's take a look at an example, right? According to a report from the Nielsen Company, 65% of internet searches in May 2010 used Google, right? A sample of 100 searches is studied. Approximate the probability that exactly 70 of the searches used Google. Well, so we want the probability of 70 successes. 70 of those searches, 70 of the 100 used Google, right? So we would do 100 to 70 here times the probability 0.65 to the 70th power times 0.35 to the 100 minus 70 power to the 30th power. Okay, and we can plug all of that into the calculator. I don't think I'm going to type all that in because I have the answer beside me, but if you plug all this into your calculator, you should get 0.0494. And so the probability is about 4.94%. So let's look at another question. What if we wanted to approximate the probability that more than 70 used those searches? Well, we could figure that out. More than 70. Well, we'd have to find the probability of 71, 72, 73, and so on, all the way up to the probability of there being 100 of them. We'd have to add all of those up. Okay, the other way we could do it is we could say 1 minus and then add up all the probabilities from 0 until we get to 70. That'd be everything. Either way, this is going to take a little while. Right? We could use Excel to do it, but again, it's going to take a really, really long time to solve this type of problem, even just using Excel, typing it in, doing that kind of thing. Is there something we can do differently? Right? So this is where the normal distribution helps, right? This is where we can use that normal approximation. If you think back to that Excel project that you did, your images should have kind of looked like bell curves. They should have kind of looked like normal curves, like the shape you've been seeing for those normal distributions. And it's because we can approximate one with the other. We can calculate a z-score using the binomial mean and standard deviation, as well as the number of successes that we're interested in. Okay. But before we can do that, we have to apply what's called the continuity correction. Okay. And the general idea here is that we have to think about how things would wind up rounding if they were decimals, okay, whether or not they're in real life decimals, right? You can't have 70.5 successes, but something like 70.5 would round up to 71, right? And so we would have to think about it in that way because we're taking discrete variables, a discrete distribution and the binomial distribution. Okay, and we are making it or approximating it using something continuous, which is the normal distribution. Okay, so before you find any z values, okay, you want to, you're essentially going to adjust your x value to be able to apply the continuous curve, the continuous normal distribution to the binomial distribution. Okay, and so we're just going to add or subtract 0.5 to x. Okay, and it should be somewhat intuitive as you see this. It sounds a little strange now at first, but once you start to get the hang of it, you'll start to understand why you would do one and not the other. And it should kind of help to make some sense. So we'll talk about some examples as we go through. Okay, so if we want to find the probability of x less than a number, okay, so then we're going to subtract 0.5. We want the numbers that are going to be less than that number if we wound up rounding, right? And so that's why we subtract that 0.5. Less than or equal to, we're going to add 0.5. Right? Because that equal to means we can be equal to that number. We want to include that piece. And so we want to include numbers that will wind up rounding to it. And so we would add 0.5. And you'll see this in a real example in just a minute. Similarly, greater than a number, we would add 0.5. Okay, because of we're looking for the area that's going to be above this x value and anything that might round to it. So we want to add 0.5 so that we're above that x value. Okay. And then greater than or equal to, we're going to subtract 0.5 because we want to get all of the numbers that would round to that next positive whole number value. Again, it'll make sense in a second when you see it. Okay. And then there's if you're doing less than or equal to, if you're looking for between. Okay, and so it's really, this is just a way of combining the two that you saw a moment ago. Okay, if it's just less than, right, or greater than, essentially. Then you're going to wind up shrinking the z values down a little bit. If it's greater than and equal to, if they have equals to bars in there, you're going to wind up stretching the interval out a little bit. Okay, and like I said, let's look at an example, or at least something here. Here we have the sample size, right? The probability of success. And x is the number of successes in the sample. We want the probability that x is greater than 40. Okay. Well, again, we could do this all by just calculating it out one at a time, but let's use the normal approximation. Okay. The mean, the expected value is just n times p. And so that's 78 times 0.43. I think I have that in my notes. I do not. That's going to give you 33.54. Okay, if we want to find the standard deviation, that is the square root of n times p times 1 minus p, or 78 times 0.43, 1 minus 0.43. Type all that in the calculator, take the square root, you should get 4.37. Yeah. So we have our mean and standard deviation. To find z, right, we're going to take the number of successes minus the mean divided by the standard deviation. Okay, or the formula is meant to write it that way. Okay. But we need x first, right? And now if we want to do x is greater than 40, okay, so let's go back and just look at our continuity correction before we do anything. Greater than 40 means we're going to add 0.5. Okay, so what we want to do is instead of using 40 for x, I'm actually going to erase that. Instead of using 40 for x, we're going to add 0.5. And so we're going to use x is 40.5. So what happens there is we're assuming if these numbers are then continuous, that numbers that are less than 40.5 are going to be equal to 40, right? 40.4, we would round down to 40. 40.3 would round down to 40. Okay, but at 40.5, now this rounds up to 41. This is the first number that would round to greater than 40. Right, and so that's why we're going to use 40.5 to find z. Okay, from z, we can calculate the 40.5 minus 33.54. That's 6.96 divided by 4.37. 1.59. Yeah. Whoops. For a z-value of 1.59, we then want to, that's going to put us right about here-ish on the distribution. We want the area that's above that. Okay, that's above a z of 1.59. To do that, we would use Excel. Remember that Excel gives you the area to the left. So we type equals 1 minus norms dist. Okay, and then type in our z-value, which is 1.59. This will give us the area to the right, the area above greater than 40, which is 0.5 or 0559. I was hoping you guys could see this part a little bit better. But I think I took away something else that I might need. Let's try another one of these so you can see how this correction works again. Kind of readjusts itself. Here again, we want to find first the mean, n times p, or 61 times 0.34. Sixty-one. Having issues writing. 61 times 0.34. It's 20.74. Standard deviation. Again, 61.34, 1 minus 0.34. You guys should be familiar with some of these formulas by now, but do keep them handy if you need them. In an effort to save a little bit of time, I'm not going to write every single one of them out every time on all of the upcoming examples unless we need to. So that'll give us 3.7 there. Now we just need our x value. Right? Since we're using the normal approximation, right, to find the probability, here we have the probability that x is going to be between or equal to, it's going to equal 20 to 24. Right? And so if we're doing less than or equal to, right, think about the numbers that will round to 20 and be equal to 20. Well, anything that's about 19.5 or above is going to round to 20. Right? And anything that goes up to 24.5 is going to round to 24. Okay, and so if we're assuming these discrete numbers are continuous, then we have to just kind of think about how we're going to wind up rounding them. And if you think about it that way, right, that explains the continuity correction. Because if we go back and we look, which one is here, we're going to subtract 0.5 from the lower number, add 0.5 to the higher number. Anything above 19.5 gives us 20. Anything below 24.5 gives us 24. And so those are going to be the x values that we use. X1 is 19.5, X2, 24.5. And so Z1, 19.5 minus 20.74 divided by 3.70. Same for Z2, 24.5 minus 20.74. That's going to give us two different Z values. Okay, 19.5 minus 20.74 divided by 3.7 minus 0.33. We'll call it 34. And then for Z2, we will get, when you divide, 1.01. Okay. So our two Z values, 1.01 is basically 1. And then about -1/3. And so we want the probability that's somewhere in between here. And it's always a good idea to draw it on the graph because you'll be able to get a good idea of whether it's going to be about 50% or whether it should be about 5%, right? And so we can calculate this then again by inserting. I'm just going to show you with Excel. It's just, in my opinion, it's just a bit easier to use in some cases. Well, I don't know if that was any better. So to find the area between the two, we have to find equals norms dist, and then we're going to use the upper Z value, which is 1.01, minus the lower Z value, which is -0.34. And that gives us an area of about 50%, 0.4768. Let's try a couple more of these. Hopefully you're starting to see how they kind of go together with the correction. Here again, we want to find x is less than or equal to 470. Okay, so here before we do anything else, we can figure this out, right? If x is less than or equal to 470, that means we want all of the numbers that will in turn wind up rounding to 470 or less. And so 470.5 rounds down to 470. So that's the last number that's less than or equal to 470. Everything else lower than that. Right? So that's the one we're going to use. And so, and again, you can go look at this. If we just do less than or equal to, that was the second one, I think. Nope, it was the first one. You're going to add 0.5, right? Which is what we did. And so either way works. I'm just trying to help you realize why you're doing it this way. Help you think about how it works. Our mean in this case, n times p, 538 times 0.86, 462.68. The standard deviation, the square root of n times p times 1 minus p. So 538 times 0.86 times 0.14, and then take the square root. You get 8.04. 8.05. And then we can find Z, 470.5 minus 462.68 divided by 8.05. 0.97. We'll just go with 0.97. We want the probability less than that. 0.97 is about right here. So we want everything over here. So that's going to be quite a bit. It should be more than 50% in this case. And so we can then insert our Excel table to calculate it real quick. Equals norms dist, since we just want everything to the left of Z, which is 0.97, 0.8340. If we round, 83.4%. I believe the next examples, we're looking a little more at, yeah. So going back to our initial example, a sample of 100 studies used to approximate the probability that more than 70 used Google. Right, so before we had to add them all up, let's see what we can get here. All right, so more than 70, this is the probability of X is greater than 70. Okay, so that means that we need to start with 70.5. Right, because we want all the numbers that are greater than 70 that won't round to 70. 70.5 will round up to 71. That's greater than 70. Okay, our mean is 100. I probably do this without the calculator. Times 0.65, which is 65. The standard deviation, I will need the calculator. The square root of 100 times 0.65 times 0.35. $4.7677. I'm really bad at reading that calculator the first time. We can then calculate Z. X is 70.5 minus our mean, which is 65, divided by the standard deviation. 70.5 minus 65 divided by 4.77. That gives us a Z of 1.15. We want the probability then that more than 70 use that. So we want 1.15 and all this area over here. All that's left now is to go to your table or to go to Excel. Because we want the area to the right or greater than, in Excel we have to do equals 1 minus the area to the left, which is norms dist, and then our Z value, which is 1.15. And so 12.5%. I'm really bad at reading that last number. 12.51%. I think there's another one here we can look at. A few more, I believe. 13% of the people in a large city used a hospital emergency room last year. Okay. So that tells us our proportion or our probability. If a random sample of 200 people is taken, approximate the probability that at most 23 used an emergency room in the past year. At most means less than or equal to. And so we want the probability that it's less than or equal to 23. Okay, we can't have a decimal number of people come to the hospital, right? But we kind of treat it like a decimal. We can approximate it with the normal distribution. right? And so what numbers will round to 23 or less? Anything less than 23.5. Anything less than 23.5 will round down to 23. And so now we just calculate all the other values. The mean, 200 times 0.13 is 26. The standard deviation is going to be 200 times 0.13 times 0.87, and then take the square root of that, which is 4.75. And now we can calculate z, 23.5 minus 26 divided by 4.75. Whoops. Negative 0.53, and I looked at it twice this time. Puts the z value about right here. And so this means this is the area that we're looking for, everything less than that. And so again, the last part you have to use a table or a spreadsheet. I'm trying to use, there's no other way to do that unless you want to do a bunch of calculus over and over again. Norms, dist, and then minus 0.53. And so this tells us it's 29.81, or 29.81%. Let's try one or two more. I believe the last example, oh, there's one more, and then another example. Here, a gardener is going to buy a package of seeds. 80% of the seeds of this type germinate. Okay, he's going to plant 90 of them. Let's approximate the probability that the number is between 67 and 75 inclusive. That means including both of them. That means the probability that between 67 and 75 will germinate. So here we have 80% of the seeds germinate, so that's going to be 0.80. And we have 90 seeds. The mean here, the expected value, the number you would expect to germinate if you had 90 seeds at 80% is going to be 72. The standard deviation, 90 times 0.8 times 0.2, and then we take the square root. It's 3.79. We just have to apply our correction to these values. If we want, again, less than or equal to, right? If we're talking about equal to here, then 66.5 will round up to 67. And 75.5 will round down to 75. Anything above 75.5 is going to be considered 76. Anything less than 66.5 is considered 66. And so these are the two values we'll use to calculate our range. And then from there, we can calculate the values at the end. Okay, so for our z values, 66.5 minus 72 divided by 3.79. Number two is 75.5 minus 72 divided by 3.79. The first one, negative 1.45. The second one, $0.92. And so a good bit of the area is going to fall in between those two. And then once again, to calculate the area, we've got to use a spreadsheet or a table. You can use the table as well. Equals norms. We want to subtract the higher z value, 0.92, minus norms dist, the lower z value, negative 1.45, 0.7477, or 74.77%. So in this last example, we're going to talk about two different ways of solving essentially kind of the same problem to kind of see which approximations, which way works out, how it works out. Okay. So we're going to ask the same question kind of two different ways. Here we have the National Health Nutrition Examination Survey reported that 30% of adults have high blood pressure. We have a sample of 200 adults, and we want to approximate the probability that 80 or more have high blood pressure. So we're going to do this using the continuity corrections. We're going to do this using what we just used for all of this previous lesson. Okay. And so here our expected value, n times p, 200 times our probability, in this case, 0.3. I say, oh, so let's set the calculator down, 200 times 0.3. That's going to be 60. Okay, the standard deviation, the square root of 200 times 0.3 times 0.7. $6.48. We want the probability that 80 or more. So that's the probability that x is greater than or equal to 80. Okay, so remember, if we want equal to, we want numbers that will round up to 80. So we want to start from 79.5. So our z value, 79.5 minus 60 divided by 6.48. Get a z value of 3.009. Okay. So let's see. We then want to plug in, this is going to be a really small probability. It doesn't even fit on the graph, you guys. We want the probability that is greater than. Okay, so if we want greater than 1 minus norms dist, I'm sorry, I'm surprised by the 3.01. Which is going to be a very small probability, 0.0013. Or a 0. Whoops, this is a 0.13% probability that 80 or more, right? If you sample 200 adults and 30% of them have high blood pressure. I couldn't remember what it was. Right, that's essentially 20 extra. That's a pretty big jump, right? So let's look at then solving the same problem in a slightly different way. Okay, we're using the same sample. Let's approximate the probability that the proportion in the sample is more than 40%. So now we're looking for the probability that the sample proportion is greater than 0.4. Okay. Think back to now the previous lesson. Right? To find our z value, we're going to use the proportion that we're interested in, the sample proportion, minus the expected proportion, and in this case, remember the expected proportion is equal to but then we had to divide by this, it was the standard error of the sample proportions, right? So we need to calculate that value. It's going to look a little similar, but it's not exactly the same. If you think about what we've been doing in this class or in this lesson, 0.3, I'm sorry, I'm going to write the formula down first. In this case, it would be p times 1 minus p divided by n. Then we take the square root. Okay, and so, whoops, that is the square root of 0.3 times 0.7 divided by 200. Whoops, 0.3 times 0.7 divided by 200, and then you take the square root. 0.0324. Okay, so now we can finish finding our z-value. The expected sample proportion, or the sample proportion you're asking about, more than 40%. The expected proportion divided by 0.0324. .086. So the original estimate, the previous estimate, the binomial, the normal approximation using the binomial gives us 3.01. This gives us 3.086. It feels like a big difference in the z-value, maybe. Right? It's not, but it might feel like it is. But let's take a look at what the probability is, just for the approximation. So we want greater than this, so equals 1 minus norms dist 3. Let's call it 3.09. 0.0010. And so while the z-value is a little different, the probability that proportion is greater than 40%, 0.0010, or about 0.10% compared to 0.13% before. And so while the z-values look a little different, the probabilities aren't that much different. And one's an approximation, and the other one's calculating using sample proportions. But it gives us the same general idea about the probability and what we'd expect. That's the end of this lesson here and this week's lessons. Next week, we'll talk a little bit about how to determine if data values are normal or normally distributed. But then beyond that, we're going to start talking about how to make estimates using probabilities, and then how to compare values using probabilities. We'll use a lot of very similar equations, and we'll talk a lot more about probabilities and questions just like this. If you have any questions for me, please reach out, and I will talk to you guys next week.